In this last part of the lecture, let's focus on how the operating system itself can act as an arbitrator to avoid deadlocks. In the examples we have seen so far, all the threads trying to access shared resources sort of know each other. They share variables, they have clear roles, readers and writers, and so on. But the threads accessing resources on a computer might be unaware of which other threads are running, what resources the latter want to access, and so on. In this sense, the operating system needs to monitor everything that is happening, and if it detects that the request of a thread could lead to a deadlock, do something about it. For instance, decide to schedule the execution of such a thread for later on. We are going to introduce a model for this setup and also mention the Banker's algorithm introduced by Dijkstra. Let's begin with the system model, which in this case relies on a graph. In this graph, we have two types of vertices, resources and processes. This is a bipartite graph. A resource can refer to CPU, memory, I/O devices, and so on. Each resource Ri has Wi instances. Since this is a graph, we also have edges. Each edge connects a resource with the process. If the edge arrow starts at the process and ends at a resource, it means the process is requesting the resource. If the edge arrow starts at a resource and ends at a process, it means the resource is assigned to that process. In the case of a request edge, we use a dashed line to differentiate an actual request from a potential request. That is, a dashed line implies the process might request the resource, but has not done yet. In our model, besides knowing which resources and processes we have and how many instances we have, we also know the maximum number of instances each process may need for a given resource. When it comes to the operating system, the idea is that the operating system should be able to distinguish which portion of its decision space is safe and which is not. In other words, which decisions might lead to a deadlock. If by deciding to give control to a certain process, the operating system allows for such a process to request a resource instance that can lead to a deadlock, then what the operating system can do is to instead suspend such a process until enough resources are freed. Suppose, for instance, we are in this situation. Process P1 and P2 could be executed next. Currently, resource 1 has been given to process 1 and process 2 has request resource 1. The operating system also knows that both P1 and P2 might request resource 2. Which process is safe to run next, P1 or P2? If the operating system decides to run P1, P1 might request and get resource 2, which is not leading to any deadlock. So from a safe state, the operating system switches to another safe state. If the operating system decides to run P2, P2 might request and get resource 2, which in this case creates a circular loop, and this might mean deadlock. So from a safe state, the operating system switches to an unsafe state. Based on these observations, the operating system can decide to run P1 and maybe suspend P2 until such a situation can no longer happen. For the model we introduced, Dijkstra introduced an algorithm for resource allocation that can avoid deadlocks. The idea is to maintain three data structures: a matrix called max, that in each position ij contains the maximum number of instances process I can request for resource j. A matrix called allocation, that in each position ij contains the number of instances already allocated to process I of resource j. An array called available, that in position j contains the number of instances that are still available for resource j. As mentioned before, the idea is to check whether potentially satisfying a request can lead to an unsafe state. How is the check done? By checking whether, by satisfying a request, the other processes can still obtain all the resources they might request or not. If that is the case, the request can be satisfied. Otherwise, the requesting process is suspended until enough resources are freed. Please notice that the operating system has an alternative to prevent a deadlock from happening, that of being able to detect a deadlock has happened and then resolve it. In other words, the operating system can decide to be reactive rather than proactive. In that case, there can be two ways out. The first one is to terminate the process that has caused a deadlock. Eventually, once one or more processes are terminated, enough resources will be available and the remaining processes will be able to continue. The second option is to select victim processes and roll back their execution. Basically, go back in their execution to a point in which the requests made by them did not result in a deadlock, and start again their execution later on when more resources are available. Usually, process recovery is a costly operation, which should be avoided to the extent possible. As always, nonetheless, the exact costs of each alternative, including both proactive and reactive ones, will depend on the specific case taken into account.